think we are.
Okay, then let's continue with Francesca Vidotto joining us from London, Ontario, telling us about the quantum life of primordial black holes as dark matter. The stage is yours.
Thank you, Benjamin, and thank you, Alessia, Luca, and all the organizers for inviting me. And it's great to be here, and it's great to share this week with all these great colleagues. Just a second that I have a return. Okay. So, very kindly, Paolo was mentioning me the other day, saying that I was going to talk about this and I was going to talk about that, except that this week is devoted to phenomenology. So I'm not going to talk about the structure of the theory that motivates the phenomenology I'm going to talk about. Anyway, please don't hesitate to ask me questions also later in the week for any curiosity about the theory itself. So, but yeah, I want to talk about phenomenology, and I want to talk about black holes. Unfortunately, I cannot talk about my other favorite subject, that is quantum cosmology. We cannot do everything, we have to choose. But I cannot resist just to highlight a couple of recent papers of mine. If you are curious about how to derive quantum fluctuations directly from the quantum theory, just computing the gravitational path integral in the sense of a discretized version of it in spin foam theory. So we have this technique to do so from scratch. And also we have ways to describe the full transition of a bouncing geometry using the full covariant theory. So these are two papers that you can look at in case you're curious about these things. You can ask me. This is just a sketch of the results, and the reason why oh, funny. So I have probably, instead of sharing my screen, I have to share, sorry, instead of sharing instead of sharing the application. Yeah. So let's see if now it works better. And what is it? Yep. And now, okay. Suck. Okay. So these are the two papers I was talking about. And the results. And one reason to mention this is the fact that by doing these calculations, we gained a lot of understanding of the meaning of computing the Lorentzian path integral. So yesterday it was mentioned this technique of Picali-Fritz in order to compute critical points. So this is used in the case of semi-classical calculations, not in the full ones that we have done numerically. And as I said, the nice thing is that we can compute correlations and hence entanglement that is a bound for quantum correlations in the early universe with a technique that is non-perturbative. It doesn't rely on effective techniques and therefore is really expected to be valid in the deep quantum regime. So this is actually my favorite thing, but with respect to phenomenology, I think that these days in the Loop quantum gravity community, the most exciting new thing is related to black holes. So I'm going to talk about this. And Carlo and I posted recently a new paper that is a review of almost 10 years of results. And I want also to highlight this other paper that just came out that was just published on PRL that propose some very interesting phenomenology that has to do with detections of primordial black holes as dark matter. And this is what I'm going to talk about. So the starting point is, of course, the fact that in loop quantum gravity, we have singularity resolution as one of the main results of the theory. This is due to the not just a space discreteness, but a space-time discreteness that prevent curvature singularities to develop. So some years ago, in fact, 10 years ago, Carlo and I applied the results that were already developed extensively for cosmology to the case of black holes, having this idea of the Planck star that simply indicates the point in which the star collapses reaches a maximal energy density. And this stage we call a Planck star. And instead, and this replaces the central singularity in black holes. And of course, dealing with this kind of process in which we have a non-singular black hole and the singularity is removed, and possibly you attach the singularity of a collapsing geometry to the singularity of an expanding geometry, namely a white hole, is something that is not new. In fact, in a sense, it has been the holy grail of quantum gravity for many years. We start with Singe in the 50s, just sketching a lot of different attempts to make this scenario work. Of course, also in loop quantum gravity, people have done this with Ashtekar-Bojewald back in 2005. Leonardo Modesto, that was here, I think, also contributed very early in this. Hayward, Stefano was mentioning here, regular black holes. So Hayward is an example of this. But what is important in the story that I'm going to tell you is the fact that 10 years ago, Carlo Rovelli and Hal Haggard were able to write a full classical metric that violates the Einstein equation only in a finite region, so that you can have a black to white transition. And of course, I wanted to remember also this work, the many works that a Spanish group has been doing, and a collaboration to which also Stefano contributed. And so here I have the main results also from the point of view of the story in loop quantum gravity. These are all the works that deals with the writing of this full metric. And again, the main novelty here is the fact that instead of having the possibility to connect a black hole space-time with a white hole space-time by going into a separated region of our universe, a disconnected region of our universe, we can have a black to white transition within our universe. So instead of talking about wormholes in which you enter and you go out somewhere else, you have indeed something that transports you somewhere else, but somewhere else in time. So you enter inside, of course, there is time dilatation in the exterior, in the interior, everything is very fast. So you just immediately came up from this process, let's say, and you are in the future with respect to everything that was outside. So this is very important for phenomenology, because if now what comes out from a black hole by a white hole phase is not disconnected from us, we can make the possible detection, phenomenology, and so on. And I want just to mention the fact that if this process happens in a time that is shorter than evaporation time, then you are a very happy theorist because there is plenty of things you can do in this respect, because there could be a very rich production of cosmic emissions. Namely, you can have different emission channels that we computed back then. You can have a high energy channel. You can have also a transmission of what is emitted at very high energy through a synchrotron emission. So you can translate what you have in very high energetic particles in the TeV into a radiation that is instead a radio emission. And this is very important for phenomenology, because if you have very high energy particles cannot travel very far away in the universe because they interact, and so they don't reach us. But if you have radio waves, those can travel really, really far and reach us and be detected. So this scenario requires an instability of the black hole, as I said, before it reaches the page time, and so we tried to verify with the full quantum computations whether the lifetime of a black hole was compatible with this. And so far the indication seems to say that yes, the process is very likely to happen, but for small black holes, yes. Sure, yes. We have careful. An event horizon means it's a teleological concept. That means that you have an horizon that lasts forever. And of course, if you believe that there is Oki radiation, this doesn't exist, because at a certain point the horizon should change, disappear, and so on. So rather than talking about event horizon, you wanted to talk about trapping surfaces. And yes, we form a trapping surface in the sense that you have a collapse, matter enters inside its own horizon, and keep on collapsing. So you have this special surface that is a trapping surface. A trapping surface, yes. No, an event horizon is something that means that the horizon is staying forever. A trapping surface, obviously. But as I said, I think if you ask to any astrophysicist, any physicist in the world, as long as they, I mean, of course, unless you have, yeah. It's a sorry, it's just a matter of words, but it's since you are asking and insisting, it's important to be precise. So one word is used for the mathematical concept. Actually, we talk about the trapping surfaces. Sure. Yes. By yes. I have a proper trapping surface. Yeah, but also, as we said, as long as you assume that there is vacuum evaporation, you cannot have, yeah. Yeah, so the point is exactly that you want to complete your Scri Plus. You want to have something to say about Scri Plus. Um, so if instead of what I was saying before, you let Hawking evaporation happens, and then the black hole gets smaller and smaller, still, this theory and this metric is telling you what happens at the end of evaporation. And as I was saying, all the calculations that we have done in the full non-perturbative quantum theory indicates that if you can let the black hole reach small size, then the transition is not only permitted, but it's what is supposed to happen. It's very probable. So we have studied also the back reaction of the Hawking radiation on this kind of geometry. And one important thing to keep in mind is the fact that so when we have the formation of this object, we have the creation of this trapping surface. At the same time, you start to grow a very large interior for this object. So the interior grows a volume that doesn't correspond anymore to the standard Euclidean volume that you will have for a given surface, but it gets larger and larger. And the older the black hole gets, the larger this volume is. So eventually, when you have, even when you have Hawking evaporation, you still have this large volume, in the sense that the Hawking evaporation is such that you close the throat of your collapsing region, but this process is faster than the reabsorption of the internal volume. So in the white hole phase, the internal volume starts to shrink, so you can get the information coming out, and you can let the fabric of the universe, let's say, leak out from this internal region. But this is a process that will take much longer than the time that the throat take to close by Hawking evaporation. Yeah. So this is important because even if you have this black to white transition, you still have an object that stays there, and this is what we call a remnant. And actually, I wanted to be careful about names again, because remnants is a very loaded concept. It has a very long history. So people have a lot of biases because they think of a particular version of what is meant by remnants. Some remnants were discarded because you didn't have enough eigenstates inside the object to account for the entanglement through the Hawking, after the Hawking evaporation. And I have just told you that here we are thinking about these remnants that have a very large volume, so a lot of microstates inside. So if you prefer, you can talk about relics. I also like the other ways of calling them, like air bones and Planckians, and I will tell you why these other names can be also appropriated. But let's just keep with the remnants. So I am emphasizing the fact that the big black holes that after this process turn into a white hole have still a very large interior. So this is important because it plays a role in stabilizing the remnants. So this is also reminiscent of an old idea that is the cornucopia that Tom Banks discussed. So the large volume is such that if you want to reabsorb the fabric of space-time that is inside, you need a time that goes as m to the fourth, where m is the original mass of m naught is the original mass of the black hole when it formed. So this is a time that is extremely, extremely long, and potentially it passes even the time of the universe itself. So if you think that the universe goes through, is a cyclic universe that goes through several bounces, this time m to the fourth can be such that these objects can stay through several eons, several times. That's why you also borrowing from Roger Penrose, I like this name of Erebones. Erebones, it's a way that Roger Penrose had in order to emphasize when these objects, that are the leftovers from black holes, pass from one eon to the other. So we have this very long lifetime, and this everything I have said has to do with a classical fact that is the very large interior. It has to do with considerations about microstates, but then there is also quantum gravity that kicks in and help to stabilize this object, in the sense that what you actually have is an object at the Planck scale. And when I talk about Planck scale, I mean a Planck area, Planck surface. And in fact, what you have is not just a white hole. What you have is more likely a superposition of a black and a white, a black hole and a white hole at the Planck scale. So, as it happens always with quantum system, when you have a two-state system, this tends to sit on the minimal energy, and the minimal energy corresponds to a superposition of those two states. So we rather have a gray hole, if you want. So the remnant, sometimes Carlo likes a lot to call it a white hole, but I prefer to call it something like a gray hole, because in fact it's such a quantum object in a superposition. And again, the minimal area that comes from loop quantum gravity play an important role, because the transition from the minimal area to nothing is highly suppressed. In the same way in which in the Bohr atom, the transition from the first orbital to nothing to zero is forbidden. So what we have in the end is something that looks very much like a particle. So that's why sometimes people like it to call it even Planckian. And the novelty, one of the novelty that came out recently is the fact that we can exploit some results that concern the possibility to put particles, massive particles, in a superposition, so that you also have superpositions of metrics, basically, because you can detect the gravitational field associated with the particle, and if the particle is in superposition, also the corresponding metrics are in superposition. So the idea is to exploit this phenomena to try to detect this particle that is this Planckian, that is a particle that has Planck sites. It interacts only gravitationally because it has lost, even if you start with a black hole with some magnetic fields, with some charge, usually in the collapse, everything gets lost. So you just have a mass that is relatively high with respect to particle physics, in the sense that it's 14 micrograms. That is like a piece of our hair. So it's small, but it's massive. It's massive to the point that it can be detected. And for instance, if one of these objects was passing through very close to our experiments for looking at superpositions of metrics, well, in our experiments, we will see a phase that, if an extra phase that the system has gained because only one of the two states would interact gravitationally with this particle passing by. So gamma is, of course, the immunity parameter, and it's always a parameter that is expected to be between 0 and 1. Yeah. Sometimes people... so you can constrain it. That's quite a long story, in the sense that there are ideas about how to measure gamma. But it's a long story, the phenomenology. I can give you the theoretical part, the theoretical motivation of the story that comes as an analogy with QCD, because this corresponds to theta QCD. So in QCD, you have an analog term that comes with a parameter that called theta, and this is always between 0 and 1. So it's expected to play the same role. I'm very happy to discuss more about phenomenology associated with gamma, because this is very interesting. It comes with chirality, symmetry breaking, and so on. Super interesting. So I should give another talk for that. Thank you for the question. So there is some excitement because in principle, it's possible to measure these objects also in the lab. Of course, rather than looking at a single interaction, so you wanted to use a big array of interacting system. For instance, you can use Josephson junction that have been already exploited for experiments with dark matter. So you have a big array of these detectors. Possibly, you can be able to see the passage of one of these dark matter particles. I have some concern because, in a certain sense, this kind of dark matter is even too good, because being massive with respect to the other proposals of dark matter particles, you really need a few of them. Like you need 3 or 4 of them in the whole solar system in order to accommodate all the dark matter. So the experiment is actually hard to make, but it's in principle possible. What are the constraints for dark matter being in the form of these remnants? There are constraints that come from the fact that if you wanted to create primordial black holes at the reheating and then have them in the form of remnants, of course they evaporate. So first they have to evaporate, and evaporation can screw up the equation of state, the balance between the matter component and the radiation component at the time of nucleosynthesis. So this gives us, this blocks us with respect to how many of these particles can be present from the early universe. And this bound is quite stringent according to some work by Aurélien Barraud and collaborator. Something that allows you to completely remove all these constraints is if you allow this object to come from a previous eon of the universe. So if you are in a bouncing cosmology in which you need not to have inflation, because of course if you have inflation, you dilute all your dark matter. So you need a bouncing model without inflation of the kind that Robert was talking about before. And then basically you have no constraints and you can have all these objects as much as you want, and you can get them passing through the bounds without any problem. So of course, in order to, yeah. I see. Uh, Of course, so there are I was thinking, for instance, of course, you don't want them to. So what you can have is that you can have. So the kind of constraints I was thinking about. Uh, no, 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 I'm getting your point, but I think there should be an answer for this, in the sense that the recollapse depends also again on the question of state of the universe. So it depends on how much radiation you have. So I'm thinking that one constraint is that you can have all the bouncing model saturated by these objects. So imagine you arrive to the throat of your bouncing model, you arrive at the point of maximal energy density, and you can imagine that at that point you only have these remnants. So of course you want to have enough of them, but I think all the calculations were indicating, so of course, all the calculations are indicating that you can have a universe that is large, still macroscopic with respect to them. So they are not to all collapsed in one thing. And with respect to the recollapse, I have to think about, because I haven't done a calculation, but my intuition is that because of the presence of radiation, and because of the presence also of the kick-in of the quantum gravity effect that provides a negative pressure. So what you have is that the universe starts with a period of superinflation that is not inflation, it's just a superinflation given by the quantum gravity effects. And there could be also the presence of a cosmological constant. So at the moment of the bounce, for sure, you get a kick. Then why does it recollapse? Then you get into the usual story of an expanding universe. So we have the standard so of course we wanted to match with the standard level of the standard amount of dark matter. So yeah, yeah. Yeah, usually we get the constraints from below, but you're right that this could be a way to, yeah, yeah. Thank you so much. I will think more about this. It's a, yeah. Not yet at this point. I will talk more. I will mention more about this. It's an ongoing. So regarding the initial condition in the before the bounce, of course, this depends on model that they are still to be constructed. So I would like to spend some time. So first of all, I'm completely lost. What time have you we start? So I have. So okay, good. So I wanted to review a few things about the primordial black holes because, of course, talking about remnants makes sense only if you think that primordial black holes are a viable option. And primordial black holes, I believe, have become a prominent candidate for dark matter these days. So let me tell you why I think it's an exciting moment for this kind of physics. Of course, so one thing is that we are seeing black holes in different sizes. And we are seeing black holes farther and farther, namely earlier and earlier in the history of the universe. So here there is a paper from last year about supermassive black holes of 16 billion of solar masses. Also, we have evidences of those mastodontic objects being already present in the very early universe, also, for instance, at the redshift equal to 10. So the question is, how could it be possible that these objects form being so big so early? And one possibility, of course, is given by a primordial formation. And then, of course, the most important evidence should come from gravitational waves, from the fact that with LIGO and Virgo, we are seeing more and more mergers. And some of these mergers may be hint of primordial black holes. So in particular, we are seeing low mass gap process. Process in which you have black holes that are just two or few solar masses, and those with a mass ratio that gets smaller and smaller. And also we have some events that possibly could be associated with primordial black holes. So here you see that the merging mass is below a solar mass. And it seems that this merging may be associated not with the merging with a neutron star, but with the merging of two black holes. So indicating, again, the primordial origin of these objects. Regarding primordial black holes, the formation mechanism could be many different. So I'm not gonna review all of them. So once you enter into the mindset that you can have primordial black holes, you see possibility to form primordial black holes basically everywhere. The most developed and the standard way in which we can have the formation of primordial black holes is through critical collapse in the early universe. So this is in particular associated with the standard inflationary scenarios in which when matter enter its Hubble horizon, starts to collapse. So you form objects that corresponds to the Hubble radius at the time of the formation. Namely, the earlier you go in the history of the universe, the smaller the black hole you can form. And then as time passes, you can form black holes that are bigger and bigger, possibly also supermassive black holes. So this is interesting for phenomenology because you can form black holes of different sizes, and you have different physics that you can prove associated to this. So the kind of phenomenology you can do with these black holes of different sizes is wide and diverse. And one interest of this is the fact that so you can form black holes with different sizes. It's important to remember that with respect to what was believed in the past, you can have the formation of primordial black holes not with a monochromatic mass spectrum. So you form the black holes and they all have the same mass, but you rather have a distribution of masses. And so you can have the interplay in dark matter of primordial black holes with different masses, and you can also have the interplay of a component of dark matter being in primordial black holes, and I don't know if you like other kind of candidates like axions and so on. The presence of primordial black holes doesn't interfere with these other species, these other kind of particles. So it's possible that you can have more than one explanation for the total amount of dark matter. One important thing is the fact that a way to discriminate between primordial black holes and other black holes is that if they form by direct collapse in the early universe, so imagine you are in the universe in which you have just a sea of very high energy photons, and these photons are collapsing, then what you expect is that they don't have spin, or they may have a very small spin. And in fact, this is consistent with some observation that has been done by LIGO and Virgo, in the fact that the black holes that we have seen so far very often don't show signature of spin. So the spin seems to be very close to zero. And there is a prediction that comes from quantum gravity there, because Johnny Bianchi, Haggard, and collaborators studied the fact that the distribution of spins in primordial black holes should be related to the black hole, to the Hawking entropy. So the microcanonical symbol for the distribution of spins corresponds to the distribution you expect from the Hawking entropy. So you have, of course, black holes that have all spins that is very close to zero, but smaller black hole can gain some spin. So the more we get information regarding black holes and possibly small black holes, the more we can try to prove this. And this will be, again, a test for quantum gravity. I wanted to conclude. Yes. Yeah. So, but because because you're thinking about, but if they start with zero momentum, because you have this. Yes. So my understanding again is that so okay, so that I haven't been working myself with this, but the way in which I understand it is that the region that collapse, it's exactly what corresponds to the Hubble radius. So, okay. So you were saying if instead the collapse was corresponding to something that is smaller than the Hubble radius, then I would have higher spin. Yeah, okay. I see. I see. Yeah, okay. So, but as you said, in this case, you had the cosmic string and then the Hubble radius that was much, much really. Yeah, okay. So, I mean, this could be a very, the spin could be an interesting way to discriminate between the origin of the formation of these objects, for sure. That's very interesting. Thank you. Yeah, okay. So you mean, so here I was just mentioning direct collapse. Of course, yeah, no, what, yeah, I had this, and the spin would be one of the variable, one of the parameter that you can check in order to discriminate between. Yeah, sure, of course. But once they are subsolar, then again you need to know how. Yeah, yeah, no, I know. But from what we were saying is from which formation mechanism? Yeah, yeah, no, yeah, of course. Okay. No, no. So my reasoning was that once you allow for them to be primordial, then and if they form through the collapse at the reheating of Hubble's K region, again, if this is the scenario that is realized, it could be a test for quantum gravity in terms of statistics of these objects. Yeah, so, oh, papa. Yes. Okay, so now the interesting, also a bit more speculative part of this story, because I wanted to relate, so in a sense, I told you about primordial black holes, and there is some pretty solid physics that has been done on this in these days. And Mario, of course, has been involved in many projects on this. And she may know even better than me all the new results and constraints. So there is a piece of solid physics. I believe also that the idea that black holes turning into white holes, at least for those objects that are at the end of the Hawking evaporation, is also quite convincing. And because of the presence of this full metric, full classical metric for the process, this is something that I hope we, as a community, we can trust, even if we disagree about details of one quantum gravity models or the other. So these are pieces of solid physics. And now I go into the speculative part because we are always tempted to put together all the things we like. So I love bouncing cosmology, and I like this idea of the remnants. So let's see how they can be together. So in loop quantum gravity, it's well known that because of the fact that instead of a big bang, you have a big bounce, you should expect the beginning of the universe a vacuum state that is not Bunch-Davis. Namely, the bouncing process excites your vacuum, and this excitation could be important for the formation of primordial black holes. So this Chinese group have been suggesting the fact that because of the specific way in which perturbations behave in a loop quantum gravity bouncing universe, you have the appearance of nonlinear effects in the evolution of the fluctuations. So this nonlinearity may lead to a different threshold, a different density contrast needed in order to start the collapse and the formation of primordial black holes. Another suggestion has come from this Greek student, Papa Nicolaou, that show the fact that again, because of the excitations of the vacuum state from quantum gravity, you can have a reduction of the density contrast up to 50%, so that you can form more primordial black holes. So the only problem of this result is that it depends on the critical energy density of the bounce and on gamma, of course, since Alessia also was asking. So, of course, here gamma plays a role. And yeah, they started to form. So imagine you have quantum fluctuations. So even fluctuations that are smaller can give rise to a black hole. So usually you have distribution of fluctuations, so some regions that are more or less overdense, let's say. Yeah, but it's the density contrast that, so you need the less density contrast in order to have the formation. Yeah, okay. Y- So you need to be above the mean density, and how much you, yeah, but how much above you need to be in order to start forming black holes. So the problem is that you have to pass a threshold. So if the threshold is lower, it's easier for good. Anyway, unfortunately, this result has a problem that it works well, but you need to be very close to the bounce. So you need to be very close to when the energy density is very high. So again, this is a scenario that was originally thought in a inflationary context, but I think it works much better if instead you are in a context without inflation, because then you can form them very close to the bounce and keep them without the dilution that comes with inflation. So this is a caveat. Uh, so a, a different possibility in a bouncing universe is that instead of forming the black holes after the bounce, you can also form them before the bounce. And for the remnants, I was mentioning that you can form them even eons before, and because they are very long living, they will stay there and they can pass through the bounce and survive. Another possibility was considered by Robert with Jerome some years ago, and they were studying the possibility to have the formation of black holes through merging during the collapse. Then this is more viable, more interesting when you form primordial black holes. I don't know what would be the amount of remnants that you get from there. That could be a very interesting question. But the point, maybe what is interesting here is that anyway, you can have at the bounce already objects that are old and that starts evaporating and evaporate fast enough so that they don't scramble the equation of state, the nucleosynthesis, and so they be remnant there later. One caveat that I keep on mentioning is whether primordial black holes can pass through the bounce. And I want you to appreciate the fact that even if you think in terms of what happens in loop quantum gravity, in which you expect the bounce to happen when you have a Planckian energy density, well, if we take the current universe, and for simplicity, we imagine that the current universe is a closed universe, and you make everything to the size of a proton, that is when you get the Planckian energy density. Well, the size of a proton is still 15 order of magnitudes, if not more, larger than the Planck length. So this means that for a Planckian or for a small black hole, there is still a lot of space to pass through. So the universe still look macroscopic for those particles at the bounce. And I have also some other ideas about how this could not lead necessarily to merging when we are close to the bounce. And one possibility could be related to the BKL conjecture, because so if you have objects that goes through the bounce, but then at a certain point they get disconnected because of BKL, so they will not feel, they will proceed through the bounce without interacting, so without the possibility of merging. So in all this, we are. So we'll skip. I think I will skip this part. And I will go directly to conclude with some comments on the matter bounce that that Robert was already mentioning and that he studied thoroughly. So the matter bounce is a possibility in which you don't have inflation, and the almost scale invariant power spectrum that you need to achieve at a later time is given by the fact that you have a matter dominating phase when the universe is contracting. Now the question is always how do you put your ingredients in your cosmological model? Where is this matter coming from? And here I'm suggesting that if you have a universe that is already filled with black holes and possibly with remnants, those can constitute the kind of matter that is appropriated then to have a matter bounce, because in fact these remnants or even the small black holes would just behave like dust, in the sense they will be pressureless, they will just interact gravitationally and without any further interaction. So the idea is to use this to study a matter a matter bounce in loop quantum gravity. So the actual bounce is produced by loop quantum gravity, but then we have a matter component that is given by these primordial black holes or these remnants that we have to model as a fluid. And then we are adding also some further fields. One field to make the ekpyrosis. So this is needed in order to account, to prevent the formation of big anisotropies. Again, for the moment, what we are doing is just putting the ingredients to have the general model. But then this extra field, of course, people originally motivated the ekpyrosis from string theory, but there could be other ways in which an ekpyrotic potential can appear, and some of them can be also motivated by loop quantum gravity. So this will be for future developments. And we are also adding some exotic matter, and here the reason for exotic matter is simply to mimic the presence of a cosmological constant. And the reason why we do this is that the matter bounce with an ekpyrotic field was studied before by Param Singh and collaborators, but what they had was a perfectly scale invariant power spectrum. If you want the almost scale invariant power spectrum that we observe, you need to add this cosmological constant that gives you the proper result. So this is ongoing. I was hoping to have this paper out already by the end of the summer, so maybe in the next weeks you may see it online. And the one nice thing also of this work is the fact that my student Matteo Pasquale has figured out all the computations. If you want a bouncing universe, so if you wanted to study the perturbation in a bouncing universe with the two fields that was not known, was not in the literature before. So again, to summarize, the matter bounce could be a very interesting alternative to inflation, and so we can get the most important feature of a cosmological model, that is the almost scale invariant power spectrum. We also, we of course have to deal with anisotropies, but it could be extremely interesting also in connection with loop quantum gravity. It could be extremely interesting in connection with primordial black holes. One 1 minute thing with respect to phenomenology and to cosmology. I wanted to mention the fact that if we have a distribution of remnants. These remnants are not just inert. They can radiate because I said that these objects on the very long term, that here is very, very long, namely it could be many, these terms M0 to the fourth corresponds possibly to many cycles of universes and so on. But through all this period, you can have some very faint, very long length radiation that is emitted, and this is what allows the information to be released from these objects, and this is what allows for the internal volume to be reabsorbed in the external fabric of the universe. So we have studied the radiation that comes from it. We have studied the possible diffuse emission. The model that we have used is very rough because we had to assume a monochromatic mass spectrum just to make the calculations, so this preliminary calculation. But I think this could be also very interesting even in for phenomenology, because this allows for some extra radiation, an extremely long wavelength radiation. And I was a bit excited yesterday hearing from Stefano about the ideas of using a very low, some effective condensate that requires very long wavelengths. So I had some ideas that maybe these things could be connected. But this is for future, and it's such a subtle effect. And the fact that these objects produce such a large number of photons of low energy is also the reason why you cannot form remnants in the lab at CERN, because this kind of process is highly suppressed. And with this, I close my review of the phenomenology associated with remnants. I hope I have given you an idea of all the possible connections between primordial black hole remnants and bouncing model, loop quantum cosmology. Thank you so much for your attention.
Thanks a lot for this nice talk. There's time for one question, yes.
So my question is, you mentioned white hole constitute. So the question, what is the metric for white hole you suggested?
Is this one. So the point is not just the metric for a single white hole. The point is to have a metric that makes the process from the black to the white hole. And so the metric that I am referring to have been developed in this paper. So the metric that you see here is the metric of a collapsing star. So here you have the matter part of the star that is collapsing. Everywhere the metric is classical, namely here you have a Schwarzschild, here you have a vacuum solution of the Einstein equation, and you have just this finite region that here is emphasized, but is actually very, very small. And just in this region, you assume that you have the actual quantum effect. So you have a violation of the Einstein equation. But so I refer in particular maybe to this last paper for the most updated version of the metric. Yeah.
Okay, there's plenty of more time in the discussion session for more questions. So let us thank Francesca again.
Thank you so much.